So today we're going to talk about Ampere's law. First of all, we're going to talk about the core concept. The current refers to the amount of charge passing through the core section of a conductor per unit time, usually expressed by the amount of electricity passing through the unit core sectional area per unit time in amperes. Magnetic field refers to the range of action of the force generated by the magnetic force on the object. It's a kind of matter with direction and size. The direction of magnetic fields is determined by Ampere's law, and the magnitude of the magnetic fields is related to the current and the length of the wire. So this is the right-hand rule. The magnetic field encircles the wire in the direction defined by the right-hand rule. Point your thumb in the direction and the current in the wire and screw your fingers. The direction your fingers screw is the direction of a magnetic point as it curves around the wire. This is a diagram that shows how you use the right-hand rule. Definition or proper introduction of the principle. Ampere's law states that the magnetic field created by an electric current is proportional to the size of the electric current, with a constant of proportionality equal to the permeability of free space. Next, we're going to talk about the Biot-Savart law. The Biot-Savart law is an equation describing the magnetic field generated by a constant electric current. It relates the magnetic field to the magnitude, direction, length, and approximately of the electric current. This is the formula, which is really important. And then here is the proper formula introduction. This is the formula that usually shows B times CL equals mu 0 times I, and mu 0 is the permeability of vacuum. It's a constant value that's 4 pi times 10 to the negative 7 H per meter, and I is the sum of current through the closed curve C. B is the magnetic field strength, unit in Tesla. dl, element arc length, representing the length of curve for a small segment, and I is a current enclosed by a path. Next, we're going to derive the formula. This is a derivation of Ampere's law. First of all, use this really important formula, Biot-Savart law, and then it shows in the diagram. Since B and dl is all a vector, it's both a vector, but it's pointing in the same direction. And B times CL equals B times CL and cosine 0, which is 1. So we get B and dl as a scalar. Then you plug. You sub this formula into B and get dl. dl is 2 pi r. So you get this formula at the end. So now we're going to do our unit analyze. Since this formula, and we know the unit for mu 0 is 1 H per meter, and the base unit for H per meter is 1 kilograms meter square per second square per amp square. And then we know 1 amp equals 1 columbias per second, and 1 Tesla equals 1 kilograms per columbias times seconds. And then we plug all these units into the formula. So we got Tesla equals kilograms over second times columbias, which is what shows here. And then, for example, when analyzing a ring current, we can think of it as consisting of many ring current elements. For each toroidal current element, we can use Ampere's law to determine the direction of the magnetic field around it. We can then stack these results to get the direction of the magnetic field generated by the entire ring current. Here's some questions. 1. How does Ampere's law relate to the border principle of electromagnetism? Ampere's law is the fundamental equation in electromagnetism that relates the magnetic field around the closed loop to the current passing through the loop. It's a crucial component of Maxwell's equations, which describe the behavior of electric and magnetic fields. Question 2. Can you explain the significance of the closed loop in Ampere's law? The answer. Ampere's law specifically deals with the magnetic field around a closed loop. This reflects the idea that magnetic fields are generated by currents circulating around closed paths, emphasizing the concept of the complete circuit. Question 3. What are the implications of Ampere's law for particle applications, such as in the design of electrical device? Ampere's law is fundamental in designing coils, transformers, and other magnetic components in an electrical device. Engineering uses it to analyze the optimus and magnetic field produced by current, ensuring efficient and effective operation. And here are some examples. A coil of diameter 0.2 centimeters is formed by a 6.28 meter long wire, and a current of 1 amp is passing it. The magnetic induction as a center will be. So we have this formula, and we know the diameter is 0.2 centimeters, which is 0.002 meters, and we have the amp, so we have the current and everything. We just plug all these numbers in. We get 6.28 times 10 to the negative 5 Tesla. Example 2. Compute the magnetic field of a long straight wire that has a circular loop with a radius of 0.05 meters. 2 amp is the rating of the current following through this closed loop. The same as we do last question, but another formula. B equals mu 0 times I over 2 pi r. And then we plug all these numbers in, we get the answer 8 times 10 to the negative 6 Tesla. Okay, so now we're gonna do the lab. And this is the website for Ampere's law simulation. And this, you can see there's a lot of scenarios you can choose. You can choose which wire you want. If I click this one, I can change the value for the inner wire current, outer wire current, and the radius to whatever value you like. And if you want, you can show the magnetic field and you can show the current to see it clearly. And then we need to draw it. And then, we can draw the magnetic fields wherever you want, and he'll show you in the graph. But in this case, we want to draw in the center. And you can, there's show calculation steps here that it'll show you the steps of calculating, and you'll get the answer here. And there's also show measurement. There's current and outer wire that doesn't display in here. You can see it here. And you want to just clear the scenario. Okay, so now we're going to share our data from the lab. This is the first one we did. We first did the current in the inner wire and see how it affects the magnetic field. And in this table, we can see that the current in the inner wire, the magnetic field is increasing when the current in the inner wire is increasing. And this matches the formula we did before. And the second one we did for it is we did the current in the outer wire. And now we can see that the current in the outer wire, the magnetic field is affected by the current in the outer wire. Here since it's decreasing. So the graph is gradually decreasing in this case, which is a true statement that we can see from the formula and the things we learned before. And the third one is we change the outer radius of the outer wire, and this is a graph for it. In this case, the magnetic field is first decreasing and then increasing, and also the outer radius of the outer wire also changes the inner wire radius and the inner radius of outer wire. It changes a lot of things. Thank you.